AP Stats. This is the first of many videos to come designed for my AP Statistics students this year, the 2019-2020 school year. What I'll be doing for my classes is posting videos onto YouTube of video lessons, so very similar to the way that I normally do these lessons in class anyway. So these are lessons that I had to whip up for online stuff. A lot of it's very similar to what I used last year anyway. So it didn't take too long for me to come up with this stuff. But we'll be doing this stuff from now on, where I'll be giving you guys some video lessons over these topics. I'll give you a combined homework assignment for multiple lessons, which normally last about a day long. So here I have a handout which contains notes for the equivalent of 3 days worth of lecture notes. See if I could try to fit it into one video. If not, I'll section it off into separate videos for each separate day equivalently. But there'll be one homework assignment for this set of 3 topics. So this will be the first half of the unit for ChiSquare Inference, which that's our next unit after the one that we technically finished before spring break happened. The one that we just technically finished was Unit 9, which covered experiments, designing experiments, and then running inference procedures specifically for experimental data. So we'll go ahead and consider that unit done, basically, since I'm not really supposed to be testing you guys anymore. Now, I think they're going to give me freedom to test you guys at the AP level, so unfortunately for you guys that are at the AP level, I might still be giving tests. At the moment, I'm still trying to figure everything out, so I'm not going to have a test for another little while. But expect a test sometime soon. There might be something to where I can kind of assess you guys. Now, for sure, I'm going to want to do a mock exam. So let's go ahead and talk about that for a second. AP exams. The district has instructed me not to give you guys specific details about how we're going to be running things until the district has made a decision on how they're going to be implementing the AP exams. But the one thing I know for sure that I am allowed to share with you guys is there will be an AP exam for AP statistics and for all the other subjects that you guys are taking at the AP level, should you decide to take it. So you're currently you're currently signed up and you've already paid to take a AP statistics exam. So College Board is going to deliver on the other end of the deal to provide an exam. The details as to how that's going to happen and when it's going to roll out and what dates and whatever that we're to expect for that to happen, that's going to be the district, and they'll send out information whenever they do. And I don't know, I'm not sure if they've already have, but to my understanding, they haven't just yet. The only thing is the format's changed, and that I'm allowed to tell you guys. It's going to be online now. It's going to be a little bit later than what was initially planned, so the calendar changed, and it's going to be shorter. So it's going to be online. I think it's 45 minutes long, and for us, it's going to be 2 free response questions only. 45 minutes means that it's going to be, if I were to do the math correctly, it's going to be 1 regular-sized free response question if I were to try to guess, and then it's another one that's a lot bigger, like a problem 6. We haven't gone over any problem 6s yet, but there'll be video footage or stuff where I'm going over problem 6s again later. So that'll be once we finish the next unit. So we have this unit, which is chi-square testing, the next unit, which is linear regression t-testing, and then we're officially done with the course. There'll be some videos afterwards to go over review topics from stuff that we haven't seen in a long time, and most likely what I'm going to do is I'm going to record the prep session topics, all 12 of them. I think I have 12 of them, and I'll be recording videos of me going over all those prep session topics. Since we're not going to have any more prep sessions, it looks like we've only gone through 2 of them. One of them was with me. The other one I think I kind of recommend that you guys didn't go to because I wasn't there. But there were 2 other ones scheduled, and those aren't going to happen anymore, most likely. So I'll be recording those and providing them for you guys and you guys only, not for the rest of the district. The plan is to finish these next 2 units. I'll record a bunch of review stuff, and then after the review stuff, we'll go over specific, like test-specific stuff before we take a mock exam. And more information on that later. So for now, we'll concentrate on this particular half unit for chi-square distributions, chi-square testing. So we're going to go over, first off, this one, which says the chi-square distribution. The next day's worth of material goes over the goodness of fit test. which if you're in AP Bio, goodness of fit is a test you've used before, I'm pretty sure. There's a claimed or a hypothesized distribution some way somehow that some biological culture or population fits or follows, uh, and we test that theory or that claim, that hypothesis, against actual observed data, experimental data, and there's a way to run a test there. So after that, we're going to go through, I think, not another test, but to talk about how to manipulate two variable data. So if we have two categorical variables, how to mess around with the data uh, for stuff like that. So that'll be the third day's worth of material. So first day's worth of material, it's going to be kind of calculator heavy. Maybe not at the beginning, but eventually we're going to want to get our calculator out. And we're going to be covering how to calculate chi-square values. Chi-square is a statistic just like a z-score statistic, or a z-score is a statistic, a t-score is also a statistic, and it has its own probability distribution. And the nice thing about all of our probability distributions that we're going to be covering in this class is that they're found in our calculator. So we'll get to that later. We'll start with the beginning of this page here. So you should have a PDF of this available to you online. So I'll go ahead and post that online with instructions on how to find that. It's going to be the same way that we normally find our lesson notes. However, they're going to be posted before the lesson actually happens, or before you actually view the video, unlike the other way around where I post them like a week or two later. But either way, we'll start off with types of data. We've been dealing with numerical data quite a bit. Now we're going to switch back over to categorical data. Now we have been working with categorical data, but we do a bunch of numerical analysis with it and create a proportion, which is a numerical quantity anyway. So we're going to study this qualitatively now, looking at qualitative data. So we'll define what a categorical variable is first off. So categorical variable is a variable that assigns each member of a population to a specific category or to a position or like a rank. And we have two types of categorical variables. So one of them is called nominal. So a categorical variable is said to be at the nominal level if the only thing we've assigned to a member of a population is a name, a category. So you're in this category, category 1, or you're in category 2, or you're in category 3, or you're this type of a population member, something like that. So we're giving to it just something that's at the nominal level, means it's simply a name, simply a label. These aren't ranked or ordered in any way, shape, or form. Now, if the labels have an associated rank or an order to them, then we say that that's going to be at the ordinal level, like first place, second place, third place, fourth place, stuff like that. Or maybe like in military, you have different ranks, sergeant, lieutenant, you have a private first class, stuff like that. So those have a specific rank involved. So those aren't just names. Those also have a bit of an order to them. Then that's going to be ordinal. If there's no order scheme, then it's simply nominal. Okay, frequency and relative frequency, these are terms we've seen tons of times. So frequency is the amount of times that particular category is observed in a data set. Relative frequency is going to be scaled for all values in the data set, and it's usually by division. It's a rate, a proportion, or a percentage. Relative frequency is like a percentage out of, or a proportion out of the whole. So frequency versus relative frequency. Frequency is the numerical value, the count, the whole number. Relative frequency is after dividing that whole number by the sample size n to get a percentage or a proportion. Okay, so number one is kind of a simple problem. We're trying to categorize these types of variables as either numerical or categorical, and then if these things are categorical, identify them further as either nominal or ordinal. So look at letter A, truck carrying capacity. Now, you're trying to think as a researcher. If I was a researcher and I'm conducting some sort of a study where the variable in question is truck carrying capacity, the physical quantity I'd probably want to measure is weight, or mass would be another. And both of those are numerical quantities that can be measured using some sort of a scale that assigns a real number to a specific value for weight or mass. So this would be numerical. Generally speaking, if it makes sense to calculate an average for this particular quantity, if it's a physical quantity that could be measured using some sort of a scale, a ruler, a protractor, something like that. If it's some physical quantity that can be measured, it's most likely numerical. And if it makes sense to find an average over a certain number of these things, then it's going to be numerical. Okay, so since that's not categorical, we don't further categorize it as nominal or ordinal, so we move on to the next one. Student ID numbers. So this is one of the trickier ones because the word number is in it. It seems like it implies that it's a numerical value, but student ID numbers, the numbers themselves really have no meaning except that it's associating on a one-to-one basis a number and a person together. So there's a one-to-one correspondence on campuses between an ID number and a specific student or a specific student name. This is categorical. It doesn't really make sense to say like, oh, if I have 10 McAllen Memorial High School students, what's their average ID number? That's a meaningless calculation to make. So this is strictly categorical. And since ID numbers aren't really ranked, this is at the nominal level. Nominal. Having trouble spell things. Okay, so letter B. MPAA ratings. MPAA ratings. If I remember correctly, these are movie ratings. Like rated, let's say for example, I don't remember what the lowest is. It's G. I was going to say E, but E's for video games. So G is the lowest. You have PG, PG-13. I'm not sure if it skips up to R already. Yeah, I think it skips from R. Then there's other ones like NC-17. That's an old school one. And there's, I don't know if there's more than that. Like there's no rating, NR. So not rated, stuff like that. So different ratings, MPAA ratings. So first off, this is not numerical. Now there might be a one-to-one correspondence with an age, but no, I don't want to consider anything at that level. This is going to be categorical strictly because we're splitting up groups of the population, or no, we're splitting up movies by the name that we're giving. It's a category, so this is categorical. Now, it might make sense to say that this is not just nominal. These aren't just names. There's a rank involved because there's an age associated with it. So maybe I do want to think of it that way. Maybe I could think of this as ordinal. There is a way that we could think of this as a ranking system, right? By least favorable for maybe family viewing versus most favorable for family viewing. So you can come up with some sort of a ranking scheme to turn that into an ordinal variable. So definitely we can consider this an ordinal variable. Let's say letter D, tree species in a forest. So if we take an entire forest and if we analyze all trees and then observe what species they are and then go ahead and create data, some sort of a spreadsheet, we will be creating a categorical variable. And this is nominal. Differences in species types or differences in species, there's really no ranking scheme there. So we would consider that strictly nominal. So what type of species is this particular tree? It's just a name that we're giving it, just a category, a simple category that we're assigning it that isn't ranked, therefore nominal. So that's basically it for number one. So there's different types of variables, categorical versus numerical, and then there's different types of categorical variables. Those that are categorized at the nominal level or those with some sort of a rank involved. So look at number two. Now, first off, before I move on to number two though, ChiSquare testing is only done for nominal variables. This is nominal only. This course is a survey. It's a pretty tough one at the high school level. So if you take statistics at the high school level, it's one of the toughest courses in my opinion that you can take here. But if you go further up in the statistics curriculum, so if you take more advanced statistics courses, they build on the different types of tests out there from much more complicated situations. There's a huge library of different types of testing situations, different types of confidence intervals and things like that. There are tests for ranked variables or ordinal variables. Chi-square testing is not one of those. So it gets much tougher to test claims about or that are made about variables at the ordinal level. So this course we just scratched the surface and we only talk about the nominal stuff. So either way, with number two, this one's going to be a graphing problem. So with number two, I'll go ahead and read it. The U.S. Department of Transportation established standards for motorcycle helmets. To comply with these standards, helmets should reach the bottom of the motorcyclist's ear or ears. The report motorcycle helmet use in 2005 overall results This is from National Highway Traffic Safety Administration, August 2005. It's an old article. Summarized data collected by observing 1,700 motorcyclists nationwide at selected roadway locations. Each time a motorcyclist passed by, the observer noted whether the rider was wearing no helmet, a non-compliant helmet, or a compliant helmet. So we have 3 categories. So this is categorical variable first off. So the data is going to be categorical. It continues to say that the coding for helmet usage is shown below. So we have NH, CH, and H. In total, there were 731 riders who wore no helmet whatsoever, 150 who wore a non-compliant helmet, so that's a bad helmet nonetheless, and then 816 who wore a compliant helmet, so a helmet that met standards. Letter A, construct both a pie chart and a bar graph that display the distribution of helmet usage responses for this 2005 NHTSA sample. So a pie chart. So for this, I'm going to need a little bit of help from a calculator. I have 3 categories of data points. Those under the NH category, the CH category, and then the N category. So I'm probably going to have to name them here. So I have NH, CH, and I'm going to make a table out of this. N, we have a total. And I'm making that kind of elongated vertically because I'm going to have to be calculating some more stuff besides just the counts. So we had a total of 1,700. No helmet, 731. So N, 731. Okay, non-compliant helmet, 153. And then a compliant helmet, 816. And I think I got those numbers right. In total, there were 731 riders who wore no helmet. Yep. So those are the numbers, and we have that total. So out of that total, I'm going to change that to a relative frequency. This is a frequency. So the values that we have here, these are frequencies. And I'd like to change that to a relative frequency. So what we're going to do is we're going to divide by 1,700, and that should give me a 1 for that last one, the total. Total should add up to 1. So then these are going to be proportions. So on the side I have a calculator. I'm not showing what I'm actually typing in because I have my physical calculator. 153 is going to get divided by 1,700, and that's 0.09 in the non-compliant helmet category. In the compliant helmet category, 816 over 1,700, 0.48. And then those that wore no helmet, 731 divided by 1,700, 0.43. And those are the proportions for each category. So pretty straightforward. So I have to make a pie chart and then a bar graph. So if you print out this handout, it's kind of easy to draw in those. I need to find a center for that circle. The pie charts are circular, so that's pretty decent where that center is kind of located somewhat. So I could start anywhere I want, and I could start vertically. And this still doesn't help, does it? Maybe, maybe not. So I think that's the reason why I made this longer than just the 2. So it's been a while since I've done this, but what you would normally do if this is a pie chart, you would change those proportions to, if you like, degrees out of 360, since a full circle is 360 degrees. So that first one for non-compliant helmets, 0.09 is 9% essentially, or it's basically the same thing. 9% out of 360 degrees, then hopefully you understand the process, is 32.4 degrees. This is going to be an angle measurement in degrees. Now why am I doing that? It's because I'm kind of comfortable working with degrees anyway. So if you remember, most of us have taken pre-calculus. 90 degrees would look like this. 45 degrees is going to be halfway between there and there. So 32 is a little smaller than 45 degrees. So this is my first category. So this is 9%, 0.09. and that's for those in the non-compliant helmet category. They had a helmet, but it wasn't. They weren't in compliance with standards. So let's talk about the compliant helmets. 0.48. 0.48 is about half. So we're talking about half of a circle, which I can calculate that anyway. So 0.48 times 360 degrees, it's going to be about 180. It's 172 degrees. So 172 degrees. 172, a full 180 degrees looks like this. 172 is a little smaller than that. So maybe it's something like that. Hopefully not something that bothers you too much. But this would be 0.48, and this is for those in the compliant helmet category. And the rest of it should amount to about 0.43 out of a whole. So 0.43 times 360 degrees is 154.8 degrees. And that should be slightly smaller than the 172 degrees, but still much bigger than the 32.4 degrees. And the total out of that would be 360 degrees. So this was 0.43. Notice how I'm keeping that as a ratio inside. And this is the N category, no helmet category. So there's my pie chart. And you'd want to, of course, give some sort of a legend or a key. In this case, no keys needed, just a title, which I can put that down at the bottom instead of at the top. And this is for helmet type. Helmet type should be decent enough. Okay, same idea here. I'll call this helmet type as well to be consistent with the pie chart. So now we want a bar chart. And on a bar chart for categorical data, x-axis will have the categories. So the categories are the types of helmet. So the title and the x-axis value match, which that might be a little annoying for you guys, but I'll leave it that way. And I noticed the largest proportion is 0.48. So I'm going to go ahead and set this at 0.5. And this will be a relative frequency. So 0.5 is where it's going to cap off. How many tick marks? It's 1, 2, 3, 4, 5. So these are 10%. So that's 0.4, 0.3, 0.2, 0.1. And the stuff in between are 0.5s. This is 0 here. And 0 only works for the y-axis, does not work for the x-axis, because x-axis right now is not numerical, it's categorical. And what we'll do is we'll give the names of each type. So depending on what type of bar chart we're working with, and I forget the names of these types of bar charts. It's been a while since I've taught those. We normally don't have to cover the types of bar charts in AP statistics, but at the CP level, the textbook that I was using last year and the year before that, we did cover the different types of bar charts that are appropriate for situations like this. And I don't remember the name of it. I don't remember if it's a Pareto diagram, but in a Pareto diagram, you draw the most frequent one first, and you go in descending order by frequency. So if I wanted to follow that procedure, which you don't have to on an AP assignment or an AP exam, I've never seen them go over Pareto diagrams and specifics like that. It's unimportant. But the largest one is 0.48. 0.48 somewhere up here. You'll draw a bar. You lead with the largest one. You don't have to shade it in. I'm shading it in just so we can make a distinction between the bars themselves and those grid lines. And this was the CH, or compliant helmet category. Next was 0.43. So we go in descending order by frequency. The next most frequent was a no helmet situation, 0.43. 0.43 somewhere around here. And I'll shade that in. This was for the no helmet N category. Oh, sorry, not the no helmet. Yeah, no helmet N category. Non-compliant helmet NH will go here. And that one had a frequency, or a relative frequency, sorry, of 0.09. 0.09 is up here, really close to 1. Something like that. And there's our Pareto diagram, or our bar chart. And that's it for 2A. Letter B. Are the data in this study analyzed at the nominal or at the ordinal level? Did I say that earlier? I might have said that earlier. This is categorical for sure. And let's see, these categories, can these be ranked? I mean, they can, but are they? There's no implicit ranking system, or none that was explicitly given. So I'm going to go ahead and say that this is just at the nominal level. These are just, we put you in one of three categories. You either had no helmet, a non-compliant helmet, or a compliant helmet. So I'm going to go ahead and call this a ordinal, not ordinal, sorry, nominal categorical variable. So there probably is a scheme that we can probably come up with that'll make it an ordinal variable, but not a big deal. This is at the nominal level. So we'll look at number 3. Number 3, this is an experiment. A 6-sided die suspected of not being fair is rolled 60 times, and a statistical test for fairness will be run. The results of the die rolls are given below, and that looks pretty bad. 11, 7, 9, 15, 12, and 6. So if we were to assume that this is a fair die, this data is working against that assumption. So letter A, complete the table below that displays the expected counts for each die roll outcome. So we know what the expected counts are. It's 1/6 out of the total for each category. In this case, total would be 60, 10, 10, 10, 10, 10, and 10. So how would we have done that otherwise? Whatever this proportion is, proportion 1, proportion 2, proportion 3, and so on. And there's 6 of them. So you would take each of those categories or each of those proportions as a sequence of proportions, PI will say. PI runs from 1 to whatever n is. There's n categories. Maybe I shouldn't call that n because n is the sample size. Let's say m, where m is just some number. In this case, it's 6. So to find the expected count, expected number 1. So the expected count for category number 1. This is E1, E2, E3 all the way to E6 in this case. How do I find EI, which is the whatever expected count? It's equal to the sample size n times the proportion for that category. That's the formula for calculating an expected count. Very simple. Whatever this percentage is, you multiply by the sample size, 60. So each of those proportions were 1/6, 1/6 times 60, and it's 10 all the way throughout. So it's very simple for this one if it's a die roll. Letter B. Sketch an appropriate display that compares expected counts and observed frequencies for this experiment. So in this case, a bar chart would probably be best. And a bar chart with 2 distributions shown side by side per category. So I'll draw an x-axis, be kind of a wide x-axis, and this is going to be roll outcome. These are categorical. We're going to have a y-axis which will measure frequency, and they're equifrequent. I'm going to say that this is, let's see, expected counts versus the observed frequencies. They're both counts. The largest count I see is 15. So I can go with 15 at the very, very top. So I can say this is 10. Actually, no, I don't like where that's placed. Say that's 5. This would be 10, let's say. And then another 5 would give me 15. And I'll just go with that. And just look at that roughly. So for the first category, rolling a 1, there's going to be 2 bars, one at 11 and one at 10. So I'm going to draw the 10 one first. So it was supposed to be 10. The next one was 11, a little bit higher. I'm going to shade one in and not the other. And I'll keep shading in the one on the right. And I'm going to eventually make a key explaining the one that doesn't have a shaded scheme or that's not shaded in is the expected. And then the one that is shaded in is the observed one. So the actual experimental value. 2 would be the next one. And for 2, expected was 10. So 10 all the way across for each of these expected ones. And then the observed was 7. 7 is lower than 10, somewhere around here. Shade that in. And there's 2. 3, which I might run out of space. Hopefully not. 3 has an expected value of 10, just like all the others. Observed, 9, slightly smaller. And shade it in. 4, expected, 10. Observed, 15. That was the most frequently observed value, which is probably the reason why they're suggesting this is not a fair die. Shade this thing in. 5. Expected count, 10. Observed count, 12. 12 is a little bit higher. Shade it in. 6. Expected was 10. Observed was 6. So it's a little bit higher than 5, somewhere down here. And there's my bar chart. So let me call this frequency. I'll give a key or a legend, whatever you want to call it. I'll draw an unshaded square and then a shaded square, similar to the shading of the other one. And this is for the expected. And this is observed. And that's part B. They didn't ask me to do anything else, just sketch an appropriate display. It's going to be a bar chart. We call this a side-by-side bar graph. So what we do, we continue this, we go further. So statisticians want to come up with some sort of an objective measure for how far off the observed distribution is from the expected distribution. And we do that category by category. What we do is we subtract observed and expected, and that's probably not a shocker. We always subtract observed and expected. So it's going to be observed minus expected in that order. And we're going to come up with some way to compare them fairly. And by fairly, we mean considering the weights at which we were expecting these things to happen, or the frequencies at which, or the relative frequencies at which we were expecting them to happen. Usually having to do with probabilities. If one's more probable than the other, then we have to scale for that extra probability. So our chi-square statistic, here's how we get that done. So observed minus expected, it's always observed minus expected, and the way that we scale for that unequal weights, in this case these were equal weights for a 6-sided die, the proportions at which we were expecting these to occur, 1/6 all the way across. So 1/6 for all 6 categories. We call that a uniform distribution, if you remember that. So this is uniformly distributed, expected at least. And if those were different weights, we square the top and then we divide by the expected. So it's observed minus expected squared, and then divide that by the expected. And we're going to do that category by category. So there's going to be 6 of those, and that's why we have a sum, a sigma notation there, because we're going to be doing that 6 total times for this particular problem, and then add all 6 of those results to give our final chi-square statistic. So here they're calling it G, or I'm calling it G, because it's for a goodness of fit test. So later on we're going to see that this changes and goes to a chi-square. Chi-square is some other distribution that mathematicians and statisticians have already established and studied very, very rigorously. So we're going to see that this goes towards chi-square distribution as n gets very large. So the larger the amount of observations, the closer and closer and closer this thing approaches towards a chi-square distribution. So the formula that we normally go with, or that's usually shown either on an AP Bio exam or an AP Statistics exam, because these are the two areas where you'll see this type of a test. So the formula sheets normally have this, but they don't call it G, they call it chi-square. Because the theorem is if the sample size is large enough anyway, if the large sample condition is satisfied, then that's practically a chi-square. So just like a z-score is practically normally distributed as long as the sample size is big enough. Same idea. So we're going to stray away from using the letter G, and we're going to use chi-square in its place. So calculate the goodness of fit statistic for this die roll. So practicing that, assuming conditions apply, chi-square is equal to the sum of the square of the differences in the observed and expected values divided by just the expected value. So we're weighting it by the expected. And we do this category by category. So I'm going to be looking at this data here and subtracting them as we see them. So this is the observed, this is the expected. So it's the top number minus the second number. We square that difference and then we divide it by the second number, the bottom number. So in this case, 11 minus 10 squared over 10. And if you've taken AP Bio, this might be, what's it called, bringing back some memories. Unless you took it this year, then. Or unless you're taking it this year, then. Well, maybe you've seen it, maybe you haven't. 7 minus 10 in this next one. So 7 minus 10, you square that and divide that by the second number, which is 10. They're all going to be divided by 10 for this particular example because all expected counts are the same across the 6 categories. So for the next, 9. So 9 minus 10 squared plus, it's something minus 10 squared over 10. So what's the next number? The next number is 12. Oh, did I get that wrong? No, I didn't get that wrong. I'm barely on the 4th one. I thought I was already in the 5th one. Next one's 12 over 10. I think the last one was 6 minus 10 squared over 10. And there's my formula for the chi-square statistic, and I got to plug that into a calculator, and that's kind of going to suck. So I went ahead and edited out where I was typing that stuff out. It was literally just me like talking and saying what I was typing. So unnecessary. But either way, that's 5.6 is what I ended up getting, and I'm pretty sure I did that correctly. So you can check against yours, and if you need to, just pause the video and try it again. But I'm pretty sure I'm getting 5.6. So that's what they wanted for this part C. So calculate the goodness of fit statistic for this die roll experiment. And in this case, it's 5.6. So then, what do we do with that chi-square statistic? So if I go back to that, this chi-square statistic is analogous to, so it's analogous to like a z-score or a t-score. So that's the x-axis value. So the x-axis value for chi-square would be chi-square, and it's going to have its own probability distribution. Usually those probability distributions are skewed, heavily skewed right. So I have trouble drawing like a skewed graph that looks something like this. Is what that would look like. So chi-square is the x-axis value. And then you have a y-axis value, which in this case is probability for that particular chi-square value. That's a PDF. So the y-axis value is a PDF. So on your calculator, there is a chi-square PDF. We never usually use the chi-square PDF. That's to find y-axis values. Now, if you want to find areas, you already understand that area is found by taking a CDF. So PDF gives the y coordinate value. We don't want y coordinates. We want the area under the curve. And the area under the curve is found by using a CDF function. Now, if you want a chi-square value, so what is this actual chi-square value equal to? If they gave you an area, then you would use, I think it's inverse chi-square. I'm not quite sure. Those are really rare problems where we have to find out the chi-square value given a area value. But I'm pretty sure the calculator also has an inverse chi-square. So those are the 3 that we normally deal with. We never deal with the PDF though. So the area function is a CDF. If I want to find the x-axis given an area, that's inverse. Those are the 2 we normally use in a calculator. So going back to that. So the chi-square approximation, like I said, that goodness of fit statistic is not exactly chi-square. It's approximately chi-square if the sample size is sufficiently large. So we start off with the expected counts. Expected counts are going towards infinity, and expected counts go towards infinity as the number of observations goes to infinity. So the sample size gets bigger, then the expected counts generally get bigger as well. If that's the case, if that number e is getting bigger and bigger and bigger, this quantity, O minus e over the square root of e, is tending towards a normal distribution. That's like a z-score. That's the z-score for the chi-square test. So that normal distribution, or that quotient, is going towards a normal distribution as the expected counts get larger and larger and larger. And if that's the case, then this sum tends towards a chi-square distribution. So there's a mathematical theorem, and that's not something we prove because that requires way higher order mathematics, heavy calculus for something like that. So I've only ever seen that proof once, but I've never actually done it myself. So just know, as the sample size gets bigger, the expected count gets bigger. As the expected count gets bigger, we can go ahead and jump towards this. Then the goodness of fit statistic tends towards a chi-square distribution. So there's going to be an expected counts condition. There's a randomness condition, and then a large expected counts condition whenever we do these types of testing. Chi-square test, or chi-square probability distribution, that's a PDF. PDF gives the y-coordinate value. The PDF is skewed to the right in every situation. The domain is 0 to infinity, so it's only on the right side. There's no negative values for chi-squares, unlike the case for the normal distribution. Normal distribution has everything from negative infinity to positive infinity. And then here we have two facts, which we rarely ever use. The expected value for chi-squares would be the degrees of freedom for a chi-square. There's a way to calculate degrees of freedom. The variance for a chi-square is equal to 2 times the degrees of freedom, which is an interesting fact. And what's degrees of freedom? Degrees of freedom, I don't think I gave that here. Not at all. So for degrees of freedom, df is equal to the number of categories minus 1. That's important. Degrees of freedom would be the number of categories minus 1. Not the sample size minus 1, like for sample mean testing. This is the number of categories minus 1. Okay, so we'll practice using the calculator for something like this. Calculate the following probabilities for the specified degrees of freedom. We have 4 degrees of freedom for letter A, and this chi-square area. So for something like this, we want chi-square CDF, and there's going to be 2 values. I'm pretty sure we're only going to be putting in the left endpoint, which in this case is 8.81, and then the degrees of freedom 4. There's more than likely going to be a drop-down menu, and the drop-down menu is going to include a lower bound, an upper bound, and then a degrees of freedom input. So then what we do is we want a calculator page. So here's like a fresh start for a calculator. I'll go ahead and press menu, add a calculator number 1. And then we want probability or statistics like we're used to. Distributions. There should be a chi-square CDF, and that's number 8. So 5, 5, 8. And like I said earlier, there's an inverse chi-square. So it's going to ask for a lower bound. It was asking for a right tail area. So the lower bound is the number they gave me because it was chi-squares greater than 8.81, so 8.81. Upper bound is infinity. Normally I just type in a bunch of 9s. Degrees of freedom 4. Press OK. And there's our area. 0.066028. That's what we're writing here. So the calculator gives me, I'm having to jump between 2 screens here, so 0.066, and I can leave it at 0.066, that's fine. So that's it for part A. So for part B, we have the probability that chi-square is greater than 2.1. Degrees of freedom is 4 again. So really what we're doing is using the exact same thing that we did for part A, and we're changing the lower bound to 2.1. And if we're changing the lower bound from 8.81 to 2.1, the left endpoint is getting smaller. We're expecting the area to increase, I think. So the area should get bigger. So we're going to get a number that's bigger than 0.066. So on a calculator, I think I could just cheat by copying and pasting what we just did earlier and changing that 8.81 to a 2.1. Press enter. We get a larger area than the one before, 0.7173. So it gave me 0.7173-ish or 4-ish if you want an extra decimal place. And that's it for that one. So these are pretty straightforward. Part C and D, we're just changing the degrees of freedom and the lower endpoint. So for letter C, degrees of freedom is 12 and the lower endpoint is 17. So we're just calculating areas for either of those situations. I'm going to go ahead and skip those. Number 5, we're going to go back to problem number 3. Problem number 3 goes all the way back here. That's the die roll problem. So now what we're going to do is we're going to calculate an appropriate statistic, or not an appropriate statistic. We already have the statistic. We're going to calculate what we call a p-value now. And a p-value would be the probability of us getting these results as extreme as they were, assuming that this die is fair. So if I try to make that simpler, assuming that this is a fair die, what's the probability that the deviation away from the expected distribution is this bad? That probability is a p-value. So we're going to check conditions for using a chi-square distribution, and I haven't stated the conditions here, but there's only two. The two conditions are the randomness condition. We must have a random sample or a random simulation or some sort of a random process. So in this case, I don't have a sample of observations. This is a just a list of random experimental values. So I'm going to go ahead and say that die rolls are random. Check mark. That's the randomness condition. I just need something to be random, and in this case it's the nature of die rolls. So these are random trials. Number 2, expected counts must be large. So expected counts must be large. All expected counts are equal to 10. We've already calculated that earlier. That was part of the problem for number 3. So what do I do with this? Is this a large number or is this not a large number? So for the expected counts condition, they need to be at least 5. I'm going to put a check mark on that because they're all bigger than 5, or they're all at least 5. So there's several categories. If we're talking about a mean problem, so x bar comma mu. So if we're talking about means, the number to remember is 30. If we're talking about proportions, so p hat versus p, the number there is 10, and there's two 10s. Now if we're talking about chi-square, expected counts need to be at least 5. So in this case, both conditions are met. All expected counts are at least 5. So we're good to go ahead and calculate a probability based off of the chi-square distribution. Find the probability of obtaining a value for g that is at least as high as obtained in problem 3. So what was the chi-square value, or the value of g? In this case, this goes towards a chi-square. And this was equal to 5 point, I think it was 6. Let me double check. Yeah, 5.6, and I should have boxed that. So they want the probability that chi-square is greater than 5.6. And this is already implying, this is under the assumption that this is a fair die. Expected counts were 10 all the way across. So that was already built into the formula for calculating this chi-square statistic. They want me to sketch an appropriate graph. Okay, so what they mean by that is I have to draw one of these things. This is chi-square. 5.6 is somewhere here. And we want the area to the right. For chi-square testing, the area is always to the right. It's always a right tail area. So that one, there's no guessing involved. Is it a left tail, or is it a right tail, or is it two tail? It's always right tail. So now I want that area. So we can either steal one of these again, which that's exactly what I'm going to do. Maybe I shouldn't do that. Maybe I should just go with and show how we get that again, because we're going to want to practice that a lot. So probability, distribution is number 5, and then number 8, chi-square CDF. So the lower bound in this case, if you look back at the handouts, 5.6. Upper bound, there is no upper bound, so infinity, a bunch of 9s. Degrees of freedom. Degrees of freedom, how many categories were there? There were 6 categories, 6 different ways a die can be rolled. You subtract 1, and our degrees of freedom is 5 as a result. Press OK. And I get a value of 0.347. 0.3471-ish. That's my p-value. And I'll box that. That's essentially what a p-value is. So they didn't call it a p-value, but that's basically what they wanted. So in this case, if you go back to, and it's been a while, it's been several weeks since we've gone over this stuff, but is this a statistically significant p-value? So statistical significance has to do with a low probability, an extremely low probability. Is 0.3471 an extremely low value, probability-wise? No. So this is not statistically significant. Obtaining a non-statistically significant p-value is going to require us to not reject the null hypothesis. So in this case, we fail to reject the notion that this is a fair die. So as far as I know, this is still a fair die. It doesn't look fair because in 60 die rolls, we had as far as between 6 in one category and 15 in another category. So why would they think this is not fair? The number of 6s is very low. And in a lot of times, if you're rolling die, a lot of games favor the outcome of rolling a 6. So if the value of 6 is really, really low, and let's say if you gave this die to maybe your opponent, they would more than likely accuse you of giving them an unfair die. So that's the reason why we're probably thinking this is an unfair die, because the number of 6s is lower than expected. Number of 6s was expected to be 10, and we got 6. But because we only did this 60 times, 10 versus 6, there's not that big of a difference, statistically speaking. And how do I measure? How do I give an objective measurement, allowing me to decide whether or not this is statistically significantly different? 6 versus 10, the p-value. So the p-value says that it's 0.3471 as likely to have occurred, assuming this is still a fair die. So that's a very high probability, not unlikely for this type of result to occur. So we would have failed to reject a null hypothesis of a fair die. So letter C. Is there enough evidence at the 5% level of significance? Definitely not. To conclude that the die is not fair? No, not enough evidence. And I went ahead and explained why earlier. Because the p-value is 0.3471, and they stated 5%. This is way bigger than 0.05. That's the reason why. And that's basically it for this particular handout. So I'll go ahead and stop it here, since that's pretty much the amount of time that we would have had for a regular lecture. That's a little bit over than that. But we'll go ahead and stop here, and we'll continue with the second part out of 3 in the next video.